Now that we've talked about the basic principles of chromatography and about why you get those different spots on TLC, let's talk more about how you would report that data. So what you would want to do is have a quantitative measurement for this, and that value is called the retention factor, or RF for short. And this is equal to the distance traveled by the solute over the distance traveled by the solvent. And to calculate the RF, you first need to measure these distances. So what you do is you take a ruler and you put it next to your TLC plate. You'll see that this is 1 unit, 2 units, 3, and 4. Now we'll measure these. So how far did compound A travel from the starting line to the spot, to the center of the spot? That's 2 units. And for B, that distance is 3 units. For the solvent, you measure it from the starting line to the solvent front, and you'll see that that distance is 4. So if we wanted to calculate the RF of A, you would take the distance traveled by A over the distance traveled by the solvent, call that S. And here that's equal to 2 over 4, and since we usually report RF values as decimals, we'll say 0.5. You can do the same now for compound B, and you'll see the distance of B over the distance traveled by the solvent is equal to 3 over 4. Convert that to decimals. So what we've shown now is that compound B has a higher RF than compound A. But what does that really mean? So what it does mean is that compound B traveled faster and further since it was more attracted to the mobile phase. And what do we know about the mobile phase versus the stationary phase? The mobile phase is a less polar solvent, such as hexanes or ethyl acetate, compared to the more polar stationary phase of silica gel. And again, this means that since compound B traveled farther, it was attracted more to the mobile phase and hence was less polar than compound A. So we'll show that here. Compound B is less polar. It travels faster in the mobile phase, whereas compound A is more polar and travels slower in the mobile phase. Okay, so what about when you're running a real reaction? Sometimes you won't just see 2 spots. In fact, if you're running a reaction that happens to have multiple side products, you'll get multiple spots. So that's what I've shown here. So again, when calculating an RF, the very first step is to take your ruler and put it next to your TLC plate. This is 1 unit, 2 units, 3, 4, 5, and 6. And now we can measure these distances to calculate the RF values. And let's label these spots as compounds A, B, C, and D. So if we were to measure the RF of A, we would want to measure the distance traveled by A over the distance traveled by the solvent. And here, that distance is 1, and the distance traveled by the solvent is 6. So that's 1 over 6, which is equal to approximately 0.17. And for the RF of B, we'll do the exact same thing. So take B over S. B has traveled 3 units, so it's 3 over 6, which is 0.50. Compound C, again, the RF is equal to distance traveled by C over distance traveled by solvent, and this is equal to 4 over 6, which equals 0.66. And finally, the RF value for compound D is equal to D over S, which equals 5 over 6, or 0.83. So what can we say about all these compounds now? We can talk about their relative polarities. And again, since compound D traveled the furthest, it is the least polar and most attracted to the mobile phase, while compound A is the most polar and most attracted to the stationary phase. So using these RF values, now that you know how to calculate them, you'll be able to report them in your lab reports, and you'll also be able to interpret them when you come across them in the literature.